Hi all. So we will be continuing with EC303 AET. So today we are going to look at module number 3 and the topic is reflection of plane wave at normal incidence. Okay. So before going to that, let's recap a bit. So we had initially discussed that the plane wave or the electromagnetic wave will propagate in a direction, and the electric and the magnetic fields will be perpendicular to the direction of propagation. So if this is the electric field, the corresponding magnetic field will be something like this, and both electric and magnetic field will have an orientation. So the orientation is, you can say, as the direction of some kind of a force which will be experienced when you stand in the path of that wave. So the force that you experience might be because of the electric field or it might be because of the magnetic field. Okay. Now we have when we did our discussion, we told that the wave is propagating in Z direction, the electric field is in X direction, and the corresponding magnetic field is in Y direction. We had assumed that directions because it is easy for us to derive many characteristics of the wave. But in general, the wave can propagate in any direction. The electric field can be in any arbitrary direction. The magnetic field can be in arbitrary direction. Only thing is, all of these will be perpendicular to each other. So we can represent the direction of propagation as AK cap, the direction of the electric field as AE cap, and the direction of magnetic field as AH cap. Okay. So wherever you see AK cap, it is basically, you are saying it is the direction of propagation. Similarly, wherever you see AE cap, it is the direction of orientation of electric field. Similarly, wherever you see AH cap, it is the direction of orientation of the magnetic field. Okay. So we are moving out of our convention that the propagation is always in Z direction, the electric field is always in X direction, the magnetic field is always in Y direction. We are not considering any of those assumptions. We are just considering now the actual propagation of electromagnetic wave. Now there are some relations between all these things. Okay. So when you take the cross product of AE cross AH, then it should be the direction of propagation. Similarly, when you take the cross product of AH and AK, that should be AE cap. Similarly, the cross product of AK and AE should be AH. You can give an example. For example, when we did an assumption AK is Z, or I will put AZ, AE is AX. So this is an example, and AH is equal to AY. So this we have assumed. So this we have already seen. So when you substitute these values in this cross product, you can see that they matches. Okay. So you know that the cross product of any two vectors will have a result whose orientation is perpendicular to both the vectors, which is correct in term for electromagnetic wave because all the three vectors are perpendicular to each other. Okay. Next, we would also like to see some notations. Okay. So if you see this notation, it means the vector is pointed out of the plane of paper. Basically, you can assume an arrow, some arrow like this. Okay, now this is coming out. Okay, so if you see it from here, you can see that it is actually the tip, which is this. Similarly, if you see something like this, so the arrow has this back tilted points. Okay, so if you see the like this, then the vector is pointed into the plane of paper. For example, let's say the arrow is something like this. Sorry. So you will have the arrow tail like this. So now if you look from here, you see this cross actually. Okay, so that is you are seeing an arrow which is to the plane of paper, and this is you are seeing an arrow which is coming out towards you. Okay, so this we will use very rigorously in our next few lectures. Okay, and the next thing is we know that, so let's say your direction of, so when you take the curve, basically how will you find the direction of the output? So what you do is, let's say this is AK, okay, this is A, assume. Okay, now when you take your right hand and you curl your finger from E to K, the direction of the thumb gives you the direction of AH. So you can see that the direction of AH will be towards you. Okay, so here I don't have a video to show you, but in the class I'll try to show this. Okay, so what you do is you curl your finger from you curl your finger from AK to AE, not the other way. Okay, so you curl your finger from AK to AE, which is the right hand fingers. Then your thumb will point in one direction, and that direction is your AH cap. Okay, similarly for all these combinations, you curl your finger from AE to AH, then the direction of thumb will give you the direction of AK cap. Similarly, you curl your finger from AH cap to AK cap, the direction of your thumb will give you the direction of AE cap. Similarly, you curl your finger from AK cap to AE cap, then the direction of thumb will give you the direction of AH cap. Okay, so this I'll try to show in the class in the video. Okay, similarly, let's say my propagation direction is something like this, AK cap. Okay, and let's say my AE cap is something like this. So now you curl your finger from AK cap to AE cap. So now you can see that the direction of AH cap is something like this, just towards the plane of your paper. Okay, so make sure you understand how you can find the directions of each of the components of the wave. Okay, right. So these are some of the preliminaries. Actually, there is one more preliminary that we will discuss while we are looking at the normal incidence. Okay, so the heading is reflection of a plane wave at normal incidence. Till now we have considered the wave to be propagating freely in an unbounded medium. There is no bound, the wave can propagate freely there is no change in any of the permittivity, permeability or conductivity, nothing is changing. Now what happens when there is a change? That means what happens to the electromagnetic wave at a boundary. Or what is the relation between electric fields at both sides of the boundary? What is the relation between magnetic fields at both sides of the boundary? This we have actually already seen in our derivations of boundary conditions of electric and magnetic fields. So we will use that boundary conditions here. Okay, fine. Or let me draw in a much more easier way. So let's say this is our boundary. Okay. Now let's assume the boundary is in x direction. Okay, so this is our boundary. Since the boundary is in x direction, I can have my one medium alongside, okay, and I have a y axis which is towards the plane of paper, so that all the three axes are perpendicular. So this boundary means, actually I am saying this boundary is something like this. It's a plane. Let me draw it neatly. Some plane like this, and this plane also extends to the other side. Okay. Okay, and let me draw it neatly. Something like this. Okay, so there is a plane. Okay, and so the plane is along y direction, so there is a y here. Okay, so the plane is along y. Okay, similarly the plane has a corresponding x direction, which is the height, which is x up. Okay, the two sides of the plane has two different mediums. Okay, so let me just draw this with a slash so that okay, so the plane is like this. Now on the right side of the plane you have one medium, and on the left side of the plane you have other medium. Okay, so on the right side of the plane I have a medium here, let's say medium 2, and the left side of the plane you have medium 1. Okay, now medium 2 has some properties, which is conductivity sigma 2, permittivity epsilon 2, and permeability mu 2. Medium 1 has some properties, which is conductivity sigma 1, permittivity epsilon 1, and permeability mu 1. Okay. Now what is going to happen is a wave which is traveling in this direction is incident. Okay, the wave has an electric field in this direction. which is along x. Okay, and if you take the cross product, the wave will have the magnetic field in this direction, which is towards the plane of, sorry, away from the plane of paper. This is AH cap. So the wave is propagating. The wave will get incident on this boundary. Okay. Now some of the wave will get transmitted and some of the wave will get reflected. Okay. Now here we are assuming that the wave is incident normally. Okay. Normally means the incident wave is actually incident at 90 degree. So the wave just comes and incident. Similarly, some wave will transmit and some wave will reflect. Okay. So this is the incident wave. This is a transmitted wave. And this is the reflected wave. We say it is normal because it is incident perpendicular to the plane. Now what is then the oblique incidence? So if you say it is incident obliquely, that means that the wave has some angle. For example, something like this. It might incident like this, and so it will reflect like this, and it might transmit like this. So this is called as an oblique incidence, where you see that it is making some angle with the axis. Okay, or it is making an angle with the plane. Here, in the case of normal incidence, it is making an angle 90 degree with the plane. So this angle is 90 degree. Okay, so the wave is incident, it gets reflected, some of the wave will get transmitted. Okay, now where is the wave getting incident? You see the point here is actually z equal to 0 and x equal to 0, or you can say it is actually z equal to 0. Okay, because the whole plane has the point z equal to 0 here, right? The x will vary up, the y will vary towards the side, but for the whole plane, or the boundary of two mediums, the value of z is equal to 0. Okay, so basically the wave is incident at z equal to 0. Okay, now this we are taking because we are just making it simpler. The wave can incident maybe at x equal to 0, y equal to 0. In that case, the necessary changes needs to be done. But here we are assuming that the wave is incident at z equal to 0. Now, when the wave incident, we know that we have already seen that this is the corresponding directions. Then the incident wave will get transmitted. So let's make an assumption that the transmitted wave, the direction of propagation is like this, okay, cap. The electric field remains in the same direction, AE cap, and the magnetic field also remains the same direction because the direction of propagation and direction of electric field has not changed. So the magnetic field will also be in this direction. Now the wave gets reflected in the medium number 1. So what happens is now the direction of propagation has changed, which is now towards minus z. Okay, and let's assume that the direction of electric field remains the same, but since the direction of propagation has reversed, the cross product of AK cap and AE cap now will have a different direction. That means AH cap will be towards the plane of paper. Okay, so now the AH cap has changed direction. Now to visualize this, I have drawn this, but just to make all these things figuratively similar, I will draw another figure in which I will not be drawing as a 3D model, but instead I will be drawing as a 2D model. So I have the plane, the axis, which is X. I have the axis which is Z. Then I have Y. This is basically Z equal to 0. Okay. Now let me draw with a different color. I have a k cap, and this is my electric field. I denote as EI, which is the incident electric field, and I have the corresponding magnetic field HI. Okay, and this is medium 1, which has sigma 1, epsilon 1, comma mu 1. Okay, and this is in medium 2, okay, which is a transmitted wave. Let me draw in a different color. So the transmitted wave will have a k cap. Let's say the transmitted wave has electric field ET, which is means for transmitted, and the corresponding magnetic field HT. Okay. Now this wave will get reflected in medium number 1. So reflection direction is a k cap towards minus Z, and the corresponding electric field is ER, and the corresponding magnetic field is HR. Okay. So basically what I said is, this is my incident wave, this is my transmitted wave, and this is my reflected wave. Okay. So from this figure, if you look at this, you see that the electric field and the magnetic field are parallel to the plane of boundary. Okay. Whether it is transmitted or reflected or incident, whatever be the case, you see that the whole, I'll state that the electric field and the magnetic field of incident, transmitted and reflected waves are parallel to the boundary. Now that's a very important assumption or very important statement, because we will see why it is, where it will come into picture. So basically EI, ER, ET, HT, HR all are parallel to the plane of incidence. Okay. So EI, ET, HI, HT, ER, HR are parallel to the plane of incidence. Fine. Now we want to find out what we are aiming at. What is the relation between all these things? Or can we find a relation between all the electric field and all the magnetic field in both the boundaries for reflected, transmitted and incident? And that's what we are going to find out at reflection of plane wave at normal incidence. Let's take one by one. Let's take the incident wave. Okay. Now for incident wave, you see that AE is along X, AH is along positive Y. Okay. We also know that we can always write EI as, we have found the solution of EI, which is basically E0 e raised to minus gamma Z. So we are assuming that in medium number 1 you have the propagation constant as gamma 1 and medium number 2 you have gamma 2. Okay. So I can write this as E0 e raised to minus gamma 1 Z into, so e raised to j omega t, the real part Ax cap. All these things are there. But here, since all electric field and magnetic field will have this component, we don't want to explicitly mention that. So we are just going to assume that the component is there. We are not going to use any kind of operations on that component. So we just say EIS is E0 e raised to minus gamma 1 Z Ax cap, because this component is present in all E and H, whether it is incident, transmitted, reflected, wherever it is there, it is same. But all other parts, E0 e raised to minus gamma 1 Z, so that can be gamma 2, E0 can be, so this is incident. So reflected, for reflected wave you will have different EI0, for transmitted wave you have different EI0. So those components are different. So only the components which are changing we will consider. What other components we won't consider. Okay. Similarly, I can write HIS is equal to HI0 e raised to minus gamma 1 Z AY cap. So why there is a Z here and why it is minus gamma 1 Z? Because the direction of propagation is along positive Z. Or you can say AK cap is equal to AZ cap. You see AK cap is along Z direction. Z direction is like this and AK cap is like this. So it is along Z direction. Fine. Okay. Now we also saw that you can relate EI0 and HI0. Sorry. So we also saw that we can relate EI0 and HI0. And what is the relation? The ratio of the magnitudes of the components of the same wave, for example in this case the incident wave, is equal to eta. So in this case we are considering it as eta 1. Okay. So this wave has another parameter. In medium 1 it has in the intrinsic impedance eta 1. In medium 2 it has the intrinsic impedance eta 2. Okay. So those are, so by using that relation I can write HIS as EI0 by eta 1 multiplied by e raised to gamma 1 z ay cap. So our two relations of incident wave or two equations of incident wave is, one is with respect to for HIS and the other is for EIS. Okay. So let's keep this relation. Fine. Now let's look at the reflected wave. So in the reflected wave, you see that the AE cap is still remaining AX cap because AE cap is in this direction and X is also in this direction. So AE cap is AX cap. AH cap is minus AY cap. Why? You see the AH cap is in this direction because it is towards the plane of paper, but you are assuming that Y is positive in this direction. Okay. Similarly, AK cap is equal to, you see the reflection is happening in this direction, but your Z is in this direction. So AK cap is minus AZ cap. Okay. So your equations for ERS is equal to ER0 e raised to plus gamma 1 z AX cap. Why there is a plus? Because this is actually minus gamma 1 of minus z because the wave is traveling in minus z direction. Okay. Similarly, I can write HRS is equal to HR0 e raised to gamma 1 z minus AY cap. So this I can write as minus ER0 by eta 1 e raised to gamma 1 z AY cap. Okay. So I can write ERS, just to summarize, is equal to E0 e raised to gamma 1 z AX cap, and HRS is equal to minus ER0 by eta 1 e raised to plus gamma 1 z AY cap. Okay. Now, if you consider medium 1, if you consider medium 1, that is the left hand side here, the total electric field is because of incident wave and the reflected wave. Similarly, the total magnetic field is because of the incident wave and the reflected wave, and since both are parallel to the boundary, I can write E1, which is equal to the total electric field in medium 1 is equal to EI plus ER. Similarly, H1, that is total magnetic field in medium 1, is equal to HI plus HR. And you see this both are parallel to the boundary, or in another way both are tangential to the boundary. Okay, so I could have written here as this is means it is tangential. Okay, fine. Now let's look at the transmitted wave. In the case of transmitted wave, you see AE cap is along positive x, AK cap is along positive z, and AH cap is along positive y. Okay, so I can write, it will be a similar equation of that incident wave. ETS is equal to ET0 e raised to minus gamma 2z, because we are looking at median number 2, AX cap, and HTS is equal to HT0 e raised to minus gamma 2z AY cap, which is equal to ET0 by eta 2 second medium e raised to minus gamma 2z AY cap. Okay. So if you look at medium number 2, the total electric field in medium number 2 is only because of the transmitted wave. There is no other waves, so the total electric field is whatever is transmitted. Similarly, the total magnetic field is whatever is transmitted. So I can write in median number 2, E2 is equal to ET and H2 is equal to HT. Okay. So we have now found out what is the total electric and magnetic field in both the mediums. And you can also see that these are tangential to the boundary. Now we apply the boundary conditions of electric and magnetic field. This we have already studied in previous lectures, which states that the tangential component of electric field will be equal to the tangential component of the electric field in the second medium. The tangential component of electric field in the first medium is equal to tangential component of electric field in second medium. Since it is a source free region, we don't have a rho v. Similarly, the tangential component of the magnetic field in first medium is equal to the tangential component of the magnetic field in the second medium. And this is the boundary condition that we have derived 2 classes back. Okay, and this we are going to apply. Now you see that the tangential component of the electric field in the first medium is the total electric field in the first medium itself, right? That we have stated here. Total electric field in the first medium is actually parallel to the boundary, which means it is tangential component. The total electric field, the sum of incident and reflected wave, is tangential to the boundary. Similarly, in the second medium, the tangential component is ET. and H1 is tangential is H1 itself, and H2 tangential is H2 itself. Okay. So I can now write E1 is equal to EI plus ER is equal to ET, that is 1, and this is actually E2. H1 is equal to HI plus HR is equal to HT, that is equal to H2. Okay, because EI is equal to EI plus ER and ET is equal to E2. So basically you are grouping it something like this. Okay. Now the wave is incident at z equal to 0. This we have already stated. The wave is incident at z equal to 0, which means we need to find E1 at z equal to 0 and E2 at z equal to 0. Similarly, H1 at z equal to 0 and H2 at z equal to 0. So I'll just represent it as E1 of 0. This is E2 of 0. This is H1 of 0 and this is H2 of 0. Okay. So E1 of 0 is equal to, let's look at this, sorry, E1 of 0 is EI0 plus ER0 from this equation. E1 of 0 is EI0 plus ER0. So this is EI of 0 plus ER of 0, which is basically EIS of 0 plus ERS of 0, which means you substitute wherever Z is there with value 0. So that is the meaning of this statement. Okay. So let's do that. So this is equal to EI0 e raised to minus gamma 1 into 0 AX cap plus ER of e raised to plus gamma 1 into 0 into AX cap. So this is equal to EI0 plus ER0. Sorry, they are not vectors because they are magnitudes in the direction AX cap. Similarly, I can write H1 of 0 is equal to EI0 by eta minus ER0 by eta. This is A y cap, and E2 of 0 is equal to ET0 along AX cap. H2 of 0 is equal to ET0 by eta 2 AY cap. So this we have derived by substituting the corresponding values of EI0, ER0 and ET0 with ET with values z equal to 0. Okay, so this is eta 1. Now let's substitute in this equation, in this one. So your E1 is equal to E2 of 0, which means EI0 plus ER0 is equal to ET0, and similarly H1 of 0 is equal to H2 of 0. So EI0 minus ER0 by eta 1 is equal to ET0 by eta 2. And these are two important equations which relates the magnitudes of incident, reflected and transmitted wave, magnitude of the electric field or corresponding magnetic field of reflected, transmitted and incident wave. Now let's do some manipulations. Let's find out how much of the incident wave is reflected and how much of the incident wave is transmitted. So we need to find out how much of incident wave is reflected and transmitted. Okay, so for that let's do some manipulations. The first equation is EI0 plus ER0 is equal to ET0. The second equation is EI0 minus ER0 is equal to, let's move eta 1 to the top, eta 1 by eta 2 into ET0. That's equation number 1. This is equation number 2. Let's add 1 and 2. So 2 EI0 is equal to eta 1 by eta 2 plus 1 into ET0. This is, you can write as eta 1 plus eta 2 by eta 2 ET0. Now if you take the ratio of ET0 by EI0, you are basically looking at how much of the transmitted wave is from the incident wave, and this is called as tau, which is called as the transmission coefficient, and this is equal to 2 eta 2 by eta 1 plus eta 2. This is the transmission coefficient. Okay, and if you subtract, let's do some subtraction, or let's do a manipulation in which we are trying to find out what is the ratio of ER0 by ET0, sorry, ER0 by EI0, which will give you the amount of reflection which has happened. Okay. So let's do one thing. So from 2 you have eta 2 into EI0 minus ER0 by eta 1 is equal to ET0. This is equation number 3. Now let's subtract 1 and 3. Okay, or basically both are same equations. Okay, so we can just equate. Since 3 is equal to 1 implies you can write EI0 plus ER0 is equal to eta 2 by eta 1 into EI0 minus ER0. Now you can verify this. You can just take the terms of EI0 common on the left side and take the terms of ER0 common on the right side. When you manipulate this, you can get ER0 by EI0, which is capital tau. This is equal to eta 2 minus eta 1 by eta 2 plus eta 1, and this is called as the reflection coefficient. And it gives how much of incident wave is reflected. Okay, so this is the expression of the reflection coefficient for a normal incidence. Okay. Similarly, transmission coefficient actually gives you how much of incident wave is transmitted. Okay. So thus we have found when the wave is incident normally to the plane, what's the relation between the electric fields on both sides, what's the relation between the magnetic fields of all the three waves, and how much amount of incident wave is reflected and how much amount is transmitted. Okay. So this is an easier derivation because it's a normal incidence. Next we are going to look at oblique incidence, which needs some kind of mathematical background. Okay. So we'll stop it here. We'll see in the next class. Thank you.